Welcome to the AI for Net Zero webinar series. My name is Amal Sheikh, and today I will be chairing the session. And I'm pleased to be co-chairing this session with my colleague, Professor Hannah Minke. And we are very pleased to have Professor Elaine Spiller joining us. We have a standard introduction for the webinar. The webinar series is designed to bring together expert innovators and enthusiasts from both artificial intelligence and sustainability domain, and definitely mathematicians, with an overarching goal to accelerate progress toward net zero targets. And the aim of the series is to engage and inform communities about the groundbreaking research and development at the intersection of AI and sustainability. We acknowledge the importance of aligning AI technology with ethical and sustainable practices, and we try to cover all the domains from energy, transport, environment, agriculture, and food system. Today, we are pleased to have Professor Elaine Spiller, who is a professor of applied mathematics at Marquette University in the US. She specializes in uncertainty quantification and data assimilation, as well as the development of statistical surrogate models for complex geophysical systems. Professor Spiller earned her PhD in applied mathematics from Northwestern University, followed that by a postdoctoral appointment at the University of Buffalo and the Statistical and Applied Mathematics Institutes. She is a recipient of the Way Klinger Fellowship and serves as an associate editor for the SIAM ASA Journal of Uncertainty Quantification. In today's talk, Professor Spiller will share insights from her recent work using surrogate model to better analyze geophysical hazard scenario. Without further delay, Professor Spiller, the floor is yours.
Thank you. Thanks for the invitation. It's always a bit weird giving these talks, by myself in a room. So please, if there are questions, feel free to interrupt me at any point. So where are we? So I'm sitting in Milwaukee, Wisconsin, which is right here. This is Milwaukee. Here is the coast of Lake Michigan, and this is the state of Wisconsin, located in the upper part of the center of the state. And if you follow our politics too closely, you recognize this. Wisconsin is the state where Elon Musk tried to buy a Supreme Court seat and failed about a month ago. And Milwaukee is where a judge just got arrested, and that's about 3 blocks from where I'm sitting right now. So this is work, this is really sort of long time collaborations with several of these people featured here. And it's a mix of computational scientists and statisticians and geoscientists, which I think is the only way you can address, sort of really challenging interdisciplinary problems is to do it with a team. And so I want to talk about this zero problem for geophysical flows. So first, let's think about hurricanes and storm surge from hurricanes. So, right, when a hurricane comes in, just from the pressure balance, it effectively pushes a bunch of water onto the coast. And here we're looking at these, the colored dots are pixels from no storm surge up to about 6 meters of storm surge. And you'll see with the hurricane, at different conditions, different pressure differences, different locations where it hits the coast will result in different inundation patterns. But it will also result in different footprints where there actually is storm surge and where there are zeros. Here we're looking on the left, we're looking at the footprints of pyroclastic density currents. So pyroclastic density currents are really rapid, granular volcanic landslides effectively. And let me trace out, so there's two simulation outputs here. So this big one that I've just traced, which is centered here. So here, where the vent opens in this caldera is an uncertain parameter in our model. And then a small flow over here. So where that vent opens, also uncertain parameter, as are the volumes, right, which result in quite different flows. And now I want to focus on these two pixels, these two locations, the black and the white ones. And so we'll notice that for this small flow, right, it doesn't inundate either the black or the white pixel there, but it gets real close to the white pixel, right? So that zero for this small flow is sort of different in character than the zero over here, right? And that's the sort of thing that we want to exploit in this work. So before we get there, I just want to sort of do a big overview of the sort of uncertainty quantification that we're going to be thinking about. And so these physical processes, these geophysical flows, are all systems of PDEs. And basically, you're interested in how the state here, U, is changing with time. And we have a bunch of parameters that we can turn the knobs and set our simulation running, right? So we have initial conditions, maybe parameters in the model, boundary conditions. And so what we're interested in is a mapping from these initial conditions, boundary conditions, parameters into the some state values or some functional of state values. Right. And so in computer model language, we say we're interested from mapping from some inputs to outputs. And typically they're not going to be, we're not interested in so much the independent variables in the system, but these parameters, again, initial conditions, boundary conditions, et cetera. Okay, and why do we do uncertainty quantification? Well, it's sort of anything you might want to answer with a model, right? So maybe you just want to approximate the model and be able to run it very quickly. Often you're interested in some kind of integrated quantity. Sometimes you want to do optimization of that model, and sometimes you want to do optimization in the set of an inverse problem, right? So just terminology that I'll be using here. So inputs, again, these are parameters, initial conditions, boundary conditions, maybe external forcing. Outputs are quantities we can experimentally or numerically measure, and it's often some functional of the dependent variable, some functional of the output, right? And we have quantities of interest we might want to look at, which are often averages or variance, or in the case today, we're quite interested in exceedance probabilities. The notation, right? So similar ideas have developed in a lot of fields, and they all have different notation. And hopefully my notation is self-consistent within this talk, but I might have borrowed some other notation along the way, right? So here we're going to think about inputs, these parameters, boundary conditions, et cetera, as a variable x. Okay, and our quantity of interest, right? So often we're interested in some integrated quantity, some expectation here. And where we have a function of x, right? This is going to be some output from our computer model. And then we have some, say, PDF of the state there, of the parameters, I should say, that we'd like to calculate this expectation with respect to. Right, so our goal here is to predict this with uncertainty. And we'd like to do that for lots of untested simulator runs, right? So the idea here, which has been around for a long time now, is to view the computer model output as a realization of a Gaussian process. So there's some original works and some more recent books that are quite good resources. Okay, so the idea is, right, we're just going to model our computer output as a random function. So here I have a 1D input and a 1D output. And maybe my specific computer model looks like this random function curve, this bold green one here. And there's nothing about this that's particularly linear or Gaussian. But if we take a slice just at one input value, then that is modeled as a Gaussian, right? So here's our sort of slice turned over, right? So y is on the horizontal axis there. And we're just thinking about that having some mean mu and then a zero mean Gaussian process. And the real sort of key in fitting Gaussian processes is getting getting the sort of right correlation structure between two different inputs, right? So this is often where the work comes in. And so we don't want, any random function, right? We want random functions that go through or are constrained by our budget of computer model runs, right? So here I have 8 computer model runs at these inputs, and these are the resulting outputs. And now I'm going to constrain myself to random functions that go through or near those points. Okay, so we're fitting a Gaussian process, right? So we have we have our design of computer model runs, and we're going to treat those as a multivariate normal with, again, some mean trend mu and some covariance sigma. And we can just write down a likelihood for that. But really what we're looking to estimate are parameters that show up in the mean trend, the variance, or just the y scaling of the Gaussian process. And again, these correlation links are range parameters. And what the work I'll present here, so you could do this with an MLE, but we'll look at mode posteriors with reference priors following the work of Guhenberger. Okay, and then we have these just plug-in estimates, right? So if I have now values for my parameters, we can plug into this conditional mean for the Gaussian process, which now would go through all of my model runs here, ym. And we also have a standard error, so effectively a variance at each untested point x star here. Right, and this is a sort of typical cartoon. You see this sort of sausage-looking plot where now I have the mean of the process that is interpolating my model runs, and I have that as a prediction at some untested value, say here 0, along with a credible interval, so here a 95% credible interval given by the variance of that process. Okay, so that was background, and I imagine somewhat in this group I was preaching to the choir, so I went kind of fast there, but hopefully that set the stage. So thinking about volcanic hazards, which is a lot of the focus of this talk, volcanic hazards really started about 125 years ago, where in the island of Martinique in the Caribbean, well, this community lived with a volcano, and it had sort of community memory of it, right, on that sort of human family timescale. And so there was some activity in the 1850s, and when it sort of turned on again in the early 1900s, they thought it would behave like it had before. But instead, it was a massive, one of these pyroclastic flows, one of these massive landslides that took out a whole town, and there were 30,000 fatalities, right? So we really want to not rely just on human knowledge when we're thinking, and community knowledge when we're thinking about natural hazards. Recently, I've been focusing on a project in Guatemala. This is Volcán de Fuego in Guatemala, and this is a very active volcano that's been active for really about the last 25 years. And we're interested in what happens, right? So when, which valleys, how big, how mobile, And ultimately, what do these inundation footprints look like? Okay, so we'll come back to Fuego. I started this work as a postdoc, focusing on the Superheels volcano in Montserrat, and that's a really nice volcano to study because there's just a quite extensive data set, and often in volcanoes and natural hazards in general, you're dealing with a paucity of data, right? Very, very limited data sets. But here we can see an annual rate, so how many flows happen per year on a log scale versus a volume of the flow, right? So here's a million cubic meters, 10 million, 100 million cubic meters. And roughly, this thing is linear, right? So we're looking at this power law model for these volumes, and we're interested in the slope of this curve, right? To think about modeling this aleatory uncertainty. So so rare events, just you know, a sort of cartoon-ish example of why we need to think about rare events carefully. So this Pareto model is much more likely to observe future volumes that far exceed the record of recent history. So if we consider 10 volumes in our record, and if we have some non-heavy tail distribution, say maybe an exponential, you could calculate the probability of the 11th volume being an order of magnitude bigger than any you've seen in the record. And that might be something like 1 in 200,000. But for a heavy-tailed model, that same probability that the next will be an order of magnitude bigger than what's in the record might be more like 1 in 100. Right, so we really wanted to think carefully about these heavy-tailed events. And unfortunately, for communities situated near volcanoes, a lot of the behavior is quite heavy-tailed. Okay, so we're really interested in what's happening here, right? What's happening a little bit bigger than what's in the record. Okay, so again, these are our questions, right? When, which valley, how big, how mobile, what's going to be inundated? And to get at things that haven't occurred, right, we're going to rely on physics, right? So we have physics of a flowing mass, and of all the different hazards I'm going to talk today, they all kind of boil down to the same set of equations, which are basically a shallow water type equation where you're looking to conserve mass and momentum, right? So when my colleague says you have a little box and just you're interested in conservation of stuff, right? That stuff can't be created or destroyed. And then you have these forcing terms, and the different models, both different models for the same phenomenon and models for different phenomenon, are going to vary in these forcing terms. So the sort of standard model for pyroclastic flows, we have this sort of gravitational forcing driving it. We have friction along the basal surface, which slows us down. So that's really our sort of measure of mobility. And then we also have friction, how the grains dissipate energy by bouncing into each other. Okay, so what this side looks like is what's going to change as the physicists play around with things. And ultimately, what we want to do is, well, we want to have, here's data from Montserrat. So the angles, the valleys that flows go down with volumes on the radius here. And here's the volumes annualized for frequency. And this is a sort of measure of mobility from flow deposits. And then we have our simulated runs of this Titan 2D model that I just showed you. So we're just looking at sort of different angles that these things are oriented at in different volumes, and you can see the footprints. And this color scale here is in meters. These flows can be very deep and fill in gullies, more than 100 meters deep. Okay, and this is the kind of thing we would like, right? And really, we started thinking about this, a while ago now, approaching 20 years ago, because at volcanic observatories, they were relying on just a few sort of one-off simulations, right? And of course, there is some institutional knowledge from these smart scientists, but it was sort of divorced from the data in a way that didn't make sense. So we combine those and we can make probabilistic hazard maps, which here we're looking at this probabilistic hazard map as a probability contour. So it's a probability of inundation for these three maps, 1, 5, and 20 years into the future. And so here each contour is going down by an order of magnitude and probability, and you can see how this is changing over time. I'm going to talk about how we make these maps, but also I just want to focus on that in my mind, one map is never the goal, right? The goal is to say, okay, if we model the volume or the frequency or the angle things go down, how do these probability contours change, right? As we change modeling our aleatoric uncertainty, how do these change? Right. So in hazard assessment, right, these are the sorts of calculations that we're interested in, right? So in exceedance probability, where we're looking at the depth of the flow is bigger than some critical depth. That could be a meter, it could be 10 centimeters. That's less important than exceeding some small threshold is really what we're interested in. So here's our indicator that we've exceeded the threshold, and then we have some distribution. So these models that I was just talking about of the data for the randomness in the system, for the how often, how large, what direction are things happening at. But then those models also have parameters in them. And we're uncertain about those models because we have relatively limited data, right? So we might want to quantify the epistemic uncertainty and the parameters in our aleatory models, right? So this is the kind of calculation we'd like to do. Or maybe we're just interested in sort of focusing on how does one parameter impact the depth of the flow, right? So maybe what I want to do is integrate over all the other parameters and just look at quickly look at, hopefully, the depth of the flow as a function of one parameter. Right, but these simulations are quite slow, order of hour to a day, so not climate model slow, but not fast at all. Right, so that very much limits what we can do with Monte Carlo. So instead, right, we want to replace these function evaluations with a cheap surrogate. Right, that's the goal, and that's why we'll do that with Gaussian processes. And here's just my standard cartoon about Monte Carlo for hazards, right? So here I have some physical scenario. I'm drawing my Monte Carlo samples. These are scenarios that lead to catastrophe. And here I count 4 out of my 30 scenarios lead to catastrophe. But then Danny or someone else comes along and tells me I'm a terrible modeler, and I should have been using this aleatory model. And in the naivest approach, you would rerun things, which is very slow. Of course, you could do some reweighting of samples you already have, but I want to impress upon you, if you don't sort of know where this red line is, that's a really hard thing to do, and in some sense, you really are forced to do more simulations. Okay. So here are, again, that map that I had, the probabilistic hazard map that I had from Montserrat. And once a suite of simulations are done, producing one of these on my laptop is a few minutes, maybe 5 minutes or something. And what we can do here now is explore different scenarios. So something I didn't get into is this paper. Actually, a big focus of the paper is involved in the frequency modeling, which is its own story for this volcano. I'm not going to go into it, but having the emulator lets us focus on something like a detailed model for the frequency of events. But here I just want to show you what happens when I think about changing the angle model. So this was for a uniform case that we don't have any preference for the directionality of the flow. And here's a preference where we go due east. And so you can see this contour has changed pretty dramatically, just changing our aleatory model, right? So here to go due east. For this volcano, that makes sense to think about because there's a bit of a horseshoe there that tends to direct things east. But things can go any direction, and there's a fair bit of mining that happens in this region, right? So this region to the northwest, where we're focused on flows that go to the northwest, is quite interesting for the local government, right? And again, we don't want to think about a static map, but as I change assumptions, here are assumptions on the probability of the directionality. How does the map change? And that's the kind of tool that we're looking for. Okay, so I wanted to get back to this issue of why reweighting or some kind of importance sampling is hard for this problem. And so I used to have this sort of cartoon example of a 100-step random walk. So I'm going to flip a coin 100 times. Heads will step to the right, tails will step to the left, and X is where we end up. And say we're interested in the probability of landing 70 steps to the right or more. It's binomial, so you can calculate it. But if we tried to simulate it, well, of course, you would, be flipping coins or having your computer flip coins for eternity and never get 70 steps to the right. But, it's a nice important sampling trick that if I use a bias coin that, gives me heads 85% of the time and tails 15% of the time, well, then I'm going to end up on 70 steps to the right most of the time. And with importance sampling, you can do this calculation quite easily. And that probability is about 2.5 times 10 to the minus 13. But if you use a poorly weighted coin, so you get the event that you want to see, but you're really missing the threshold, and you end up with a terrible estimator, right? And this is kind of the issue that that you have to end up somehow sampling the threshold, right? And then 1D, that's easy to see, but when we have many input dimensions, that's quite tricky. I think a thing that's really tricky for a whole map is that what that threshold would look like very far up valley is going to be quite different than what that threshold looks like down valley. So if you devised a really good sampling reweighting strategy up valley, that's going to, by definition, be a poor one down valley. Right. So a clever sampling strategy alone cannot save us, right? And it could actually be quite a bad solution. So instead, we're going to use surrogates to be able to do Monte Carlo just very cheaply. Okay, so that's what we're doing then, right? So we have H here as a cheap approximation of the H from the model, so our inundation depth. And then we can explore aleatory models, right? So we can spend our time really focusing on modeling the scenarios that lead to hazards, and then quantifying uncertainties in those models. All right, so back to the zero problem, right? So this is just a cartoon function out of one of Dave Higdon's papers, and here we've just modified it so that the function output is positive or 0, right? And of course, Gaussian processes have full support, right? Minus infinity to infinity. But if we're thinking about this, if we're thinking about a function like this at every pixel or every map point, well, that boundary is going to change, right? And the number of zeros is going to change. And so this is just a tricky problem to begin with. But then also, going from something positive and curvy to something flat at zero is a really strong non-stationarity, right? But so you just mentioned these different zero boundaries, and sort of where the stationarity kicks in is going to differ for different map points. And there's lots of clever strategies to try to deal with non-stationarity. And but again, they're all going to be somewhat map point specific. And not that I think particularly it might be interesting to play around with something that we're going to look at along with deep GPs or two-layer GPs. But but for now, it's just a hard problem for some of the technology that's out there to handle. Okay, so here's the idea for this zero-censored Gaussian process, that we're going to model our flow depth as a maximum of 0 and a latent Gaussian process, where we're forcing that latent Gaussian process to take on negative values where the design response had given us zeros. Right, so we're going to impute negative responses at designs points, at runs where we had 0 responses, right? So we're going to index those 0 responses by J0 and impute values, negative values at those design points. So that's our idea. So we have to begin, so we're just basically going to use a substitution sampling. So we're going to begin with a set of negative samples. We do that in various ways, and but then onto the algorithm. So we're going to fit a Gaussian process to positive output runs and estimate the parameters of the Gaussian process, so those associated with the trend and the range parameters. And then we're condition the Gaussian process on all but one of the negative responses. So we'll pick a negative response like this one and leave it out, condition on all the rest, and then sample there. And the sample there, because we're at just one design point, we can sample from an inverse CDF of that truncated normal to get a negative sample. And that's quite efficient. And then we're going to repeat this for all of our zeros. So we'll put that one back in with its new sample and pick another one, repeat this process, and repeat that, n times, and then take an average to get the imputed runs that we see here, say on this toy function. Another thing we could do, and that proved kind of useful when we were playing around with it, is to put into this loop a stage where you don't just fit the Gaussian process to the positive runs, but you pick some of the nearest zeros to include, right? So you on this picture, it's going to be roughly these, and because those are giving you a fair bit of information on the near misses, right? Which is really kind of important, and they will then we can use those then to estimate the trend and the range parameters. And there's a lot going on in this figure, but let me try to talk through it. So we came up with this metric of what nearest is. So in some sense, how close are you to something that's positive, right? So that's this scale. So close is down towards 0. But then some of the close ones had a really high probability of being a negative response. So those weren't as interesting as the ones that had a small probability of being a negative response. So if we take that subset of the zeros and include those in fitting our Gaussian process, we end up with, and again, there's a lot going on in this picture, but basically, if we don't do that, we get the blue here for the range parameters, and if we do, we get the orange, and the true values. Oh, actually, no, those are for the two parameters. So the blue is for the x1 range parameter, and the orange is for the x2. If we just fit to the positive, we get these dashed lines, and if we fit to the positive plus these sort of nearest zeros, we get these solid lines. Okay, so you get some change in what those range parameters look like by including these nearest zeros. Okay, so let me move on to some of the results here. So we've applied this to estimating storm surge. And so here we have our design for these storm surge simulations. Right, so there are, I guess, 5 parameters here, along with the latitude and longitude of where the storm hits, right? So those are in blue along the west coast of Florida here. And then these black points are where we collected the storm surge depths that we want to model. Okay, and here what we did is for each of these pixels, we ran through this Gaussian, the zero Gaussian process, and put that onto a cluster as a pre-processing step. And now we have negative values where there were zeros for each of those runs. And here's our simulated depth, our predicted depth, which, you know, eyeball looks quite good. And here's the difference in the two, the error between the predicted and simulated, which seems quite reasonable. If we look at the fitting this with the zero Gaussian process and PCA to deal with the spatial aspect versus just a Gaussian process with PCA, well, we see a histogram of the error, and that the ZGP is doing decently better for a small error. And now if we look at the sort of tails of the error, so when we get to larger errors for our prediction from these two different Gaussian processes, we see that that the Gaussian process with PCA just really has a harder time with bigger errors than the ZGP. Okay, so on to this volcano example, right? So here, again, we have these, you know, 2 examples of the simulation footprint, and we have, I guess, really 5 the way it was written. So where the location of these events, which certainly is driving the flow, as is, sorry, I lost my mouse, as is the volume, the vent radius, which comes from 2 parameters, vent radius and flux, and the basal friction, which was, again, that how much is the ground slowing down the flow. So it's a measure of mobility. And here, these are outputs at those 2 road points. So these were points on the road, that's not on here. This black and white point. And I just want to sort of point out, you know, how this approach is helping us. So for the top 2 pictures, we have a Gaussian process just fit to positive output. For the middle, we have a Gaussian process fit to positive output, and just a sort of subset of the closest zeros. And on the bottom, we have the ZGP. And this is, you know, in some ways what really motivated the ZGP, the sort of naive things you would do, the top, and a little, you know, a little bit better, including some near zeros, you get this sort of rebound halo where the Gaussian process isn't really well constrained, right? So you're going to get some spurious flow away from where you have positive outputs. And here, I know it's quite small on the screen, but you can see some red points are the positive outputs and white points are the zeros. So again, on the top for these two different road locations, there's no zeros constraining it, and we get a lot of rebound where it should be zero. Including just some zeros, we still get a fair bit of rebound where there are other zeros. But with this ZGP, the zero-censored Gaussian process, we can see that we don't have that same rebound issue, right? Which is really kind of key. And I should have mentioned here these are kind of tricky points because we're on either side of the caldera rim, right? For these two different road points. And that's what that black curve is there, the edge of the rim. Okay, and again, focusing on those 2 points, then we can think about probabilities for different aleatory scenarios. So here for event opening, so we looked at a model from this Clark paper, and then just a uniform event opening over this this big red rectangle. And we can think about the probability of a PDC conditioned on a volume of at least this much on the x-axis here, and look at what those probability curves look like for those 2 points. Red again is for road point 1 and black for road point 2, and under the 2 different vent opening models, right, which sort of switches their probability, you know, which is the kind of thing that someone doing civil protection, you know, would want to explore, right? That's what we're looking, the sorts of problems we're looking to help answer. Okay, so I want to quickly sort of move on to a problem I've been working on more recently as motivation. I'm actually not going to talk too much about it, but that's looking at debris flows that happen after forest fires. So after a forest fire, the soil becomes quite water repellent, and what would have been a clear flow from a rainfall will pick up lots of this burnt debris and ash, and can bulk up by an order of magnitude and cause a massive mudslide, effectively. So this is just looking at 3 different rainfall intensities, and using, again, one of those, you know, sort of version of that model I showed you that's specific to debris flows. And but the moral of this picture isn't how I got this, but that there's about 1.7 million pixels here. And so doing stuff pixel by pixel, even, you know, putting it onto a cluster is not going to be very useful to help us deal with the zeros. So here what we've done is use the parallel partial emulator to think about the Gaussian process spatially. And I don't want to dwell on this too much, but just these are really the sort of same pieces that we've seen before, although I think I did change my model output here from Y to D, but hopefully you'll forgive me. So here we have P input dimensions, we have N model runs, we have some basis for the trend. We have now an N by N correlation function, and YD is an N by S matrix of outputs. So here, N is our number of simulations, and that's going to be still relatively small, right? So this correlation matrix is relatively small because you're assuming a shared correlation structure amongst inputs. But we're going to be predicting at, we're going to be predicting at S locations, right? So for us, S is going to be very big. In that picture, it was, you know, 1.7 million pixels effectively. So here are the takeaways, right? So I have one set of correlation parameters shared by all S outputs. There's just two inversions they're cheap also because they're small relative to the spatial size. Some things here the parallel partial emulator assumes is that the output is treated spatially as independent. And sort of a big thing that's really attractive from a physical modeling perspective is that the mean of this parallel partial emulator inherits conservation properties of the simulator. So if the simulator conserves mass and momentum, et cetera, then the PPE is also, up to some sampling error going to conserve mass and momentum. Okay, so if we rewrite, though, this predictive mean here, this looks very much like our predictive mean for 1D output, almost identical. And the difference here, right, is now I have this my N model runs at S locations, right? That's really the key. And I'm also going to now have S parameters for the spatial mean, or excuse me, for the mean trend. So I guess it is a spatial trend then as well, where they each have their own parameters associated with that basis function. Right, so it's just really this multidimensional best linear unbiased predictor. Each output dimension has its own mean, and each output dimension also has its own scalar variance. Okay, so back to this picture, right? So we just blindly apply this PPE to this 1.7 million pixels. And now I'm going to look at 2 pixels. So one that's kind of high up, and then one that's down here in the fan. And these are just leave one out predictions for those 2 pixels of this 1.7 million. And so for these deeper flows where there's almost no zeros, this PP is doing a pretty good job. So here we have the true values that were left out in red, and the predictions along with their credible intervals in black and blue bands. Where we have more zeros, right, this just sort of blindly applying the PPE doesn't seem to be working great, right? So we don't have, our coverage isn't fantastic, and we're doing sort of a particularly bad job at predicting zeros, as we might expect. One thing to note is this is only 64 simulations with 6 different input parameters. So this is also, could use some more design runs on this particular example, but this is a problem, right? And this is going to motivate sort of what we're trying to work on now. So back to Fuego. So what we're looking at here is runs down a specific valley or barranca. And we're not looking at depth of the flow, but we're really just looking at how many of the 300 design runs inundate each pixel that's colored, right? And so, in this valley, all of them get inundated by every run. There's a good chunk of this footprint that gets inundated by about half of the design runs, and down here are fewer, but still, roughly most of the pixels here are at least 30 or so runs. So this red line that's cutting through it is a road, and this is a road. The road is sort of at the base of a town up here, and the road is something that would get closed during evacuations, right? Or might get closed during a paroxysm during a time of high activity, but also would be a route for evacuations, right? So this is high interest locations, and here for this road, there's roughly 400 or 500 pixels that trace out that road. I should say there's about 900,000 pixels that are plotted for this output. Okay, so our idea here, and I just actually got these road coordinates yesterday, so no results on that yet. But the idea here is to do a spatially sampled ZGP. And so Fuego will be our testing ground for that. And but just for these cartoons, I want to show you to give you an idea of this. We have 88 design simulations, and each of them has 20 pixels, right? So each curve here is a result of one of these 88 simulations. There are 3 parameters that are being varied in these simulations. So volume, mobility, and the duration. How long does how quick is the material expelled from the volcano? And again, these are 20 locations, just a slice in latitude from, I guess, from north to south here. And 71 of these 88 have some latitudes with zero flow. And we can see here, this actually ends up being a little bit of a complicated example case, because some of these dip down to 0 and then come back in this sort of area of the latitude. And some of them, of course, you know, there's a you know, in the teens that are positive at each of these latitudes, right? So so bear with me on this sort of proposal for a spatially sampled ZGP. It's just a lot of text here. But we begin where we began the last time, where we have negative samples at all responses. And here I'm, instead of a negative sample when it was a scalar output, I'm going to think about a negative curve, or a curve that's at least partially negative. Right, so we're going to fit a PPE to all of our design runs to get our emulator parameters. Then we're going to condition the PPE on all but one of the negative response curves, right? So I'm going to be going through all of these other response curves, but just pick out one that has some zeros. And in that one negative response curve, then I'm going to fit a spatial Gaussian process to that one curve that we've picked out. And then I'm going to sample negative responses. We're just going to think about it at 1 pixel along that curve. So now this sampling in step 4 here is identical to what we did in the scalar output zero Gaussian process, right? So I'll sample this one negative output via an inverse CDF, and maybe 2. Maybe I'll do one that's very close to the edge. And now that I have these 1 or 2 negative samples, I'm going to fit that spatial Gaussian process for this curve to the positive outputs plus these negative samples that we just had. And then we'll sort of repeat through this whole cycle. So let me show you this cartoon that we're thinking about. So here's one curve, right? So this is one design curve that had some zeros. So the zeros were over here. But the positive values are over here, so they're not going to change in this. So we fit a spatial Gaussian process, so here in latitude, and then use an inverse CDF to, and again, with the inverse CDF, it's an inverse CDF over these parameters, right? So for one, volume, mobility, duration. Okay, so we get these negative samples, and now we fit a Gaussian process that's constrained to go through these. And this isn't a rough process. It's just that our grid is showing up with it being connected there. All right, and one thing, so we only need one of these samples, but we need one that's negative everywhere we're interested in. So here we see sort of grayed out samples that we drew from this spatial process, but those wouldn't be candidates, right? We would just pick one of these colorful samples. And then this would go into, be imputed into our data set, and we would pick another curve, right? So this is a different curve from a different simulation, and we repeat that process. We go to some other location, get an inverse CDF sample, then condition to go through our spatial process, and then pick off a negative curve to impute. So that's the idea, but this is still very much a work in progress for my student Joey, who's finishing up this summer. So with that, I will wrap up. So introduce this idea of the zero Gaussian process, which can be done in this sort of pre-processing way. Just stick it on a cluster. It's sort of naturally handles the non-stationarity of the semi-binary data that we see in natural hazards, and we can easily plug this into existing GP methods once the imputation is done. And what I just described in progress is a spatial sampling strategy for the ZGP, which I think has some promise to help our work at Volcán de Fuego in Guatemala. And with that, I will wrap up.
Thank you, Elaine, for this very interesting talk. A reminder for those who are joining us through YouTube, you need to be logged in to your Gmail account before you can post your questions, and then we can have it here in our comment box. So we start by the room here. Hannah, do you have any questions?
Yeah. So I was thinking about your fire and debris workflows. They sort of hint at compound events. I was wondering if in the future you're going to do any work on some like compound hazards, like hurricane-induced landslides or volcanic ash and cyclones. Like, where do you see as the next test bed for your GP?
Yes. Yeah, absolutely. So the fire to post-fire debris flows is something I've been working on, and we have a project now that is working with communities in rural Arizona, and the idea is that the right time to think about the sort of cascading hazard is before the fire happens, right? And so that's very much in our minds is thinking about models of fire and how they might change the landscape in ways that would lead to these debris flows, and then also how those might change if there are some mitigation actions taken, right? Some thinning of the forest, or some culverts built to try to divert flows, right? So these are and absolutely, this is something that should be happening before before the cascading hazard. Yeah.
Thank you, Elaine. I have one question from my side about trying to find the interface between hazard and non-hazard. And if I understand correctly, the problem is the continuity of the surrogate model.
Yeah. That's yes. It is the right. So it's not an issue. It's not an issue for the physical model, right? It's just going to stop when it stops. So it has no problem with not inundating a location, but it is effectively the continuity of the surrogate that's challenging.
And can you mentioned that you can actively sample around that region?
Right. So the idea is, so a lot of, and sorry, I'm going to go back quickly here. So a lot of modeling work on this is to assume, which is totally reasonable, to assume my model is either zero or this positive Gaussian process, and I think the drawback of that approach is it doesn't distinguish a zero that's a near miss and a zero that's not, right? And the idea of imputing and trying to get something that is in line with the sort of natural extension of the positive Gaussian process is to glean that information from the zeros, right? So which zeros are near misses and which aren't.
And now I will fall into the fallacy of prior work I did.
Sure, sure.
So it comes to my mind that one of the machine learning models which really focus on the interface between in classification, it focus on the interface of between the two classification, very classical machine learning or vector machines,
right?
Where they identify the points from the training data set, which is closest to the interface, and this is the only point which comes into to somehow to define the interface, and the rest is somehow excluded automatically.
Right.
Yeah, but when I worked on something like that, some of the cases was that I don't know where is the interface, so the interface is sometimes is missed.
Right.
Or and is that challenge which exists in the in these kind of problems you are dealing with, where the hazard interface are not hit by any of your data set points? Or
oh yeah, yeah. I mean, so yes, that does happen. So let me go back to the Fuego stuff. So we've spent a better part of a year on the design of this simulation set. And there were a lot of those questions, and there are two different physical models. This I'm showing you just output from one of them here that tends to overbank and spread more, which actually is something that happens physically, but it's kind of a different process that's not included in this model. Versus a model that stays quite channelized and can get sort of further extent. But I'm not sure if you can, up here, just at the edge where I have no simulations, there's quite a big town, right? And so so there's just this sort of dilemma between, okay, can, how unrealistically large, even if it's feasible, but not something anyone expects to happen. Can I force this simulation? But then there's there's no validation on it at that scale, right? And so it is really this sort of balance of what is feasible in the geological record, what is a model capturing, what is it not capturing, and can we at least even just roughly validate that to extent that we're all comfortable with, right? But that means that there are locations where there are no simulations, right? And so all we can do there is basically put a bound on the probability, and that's where we're at.
Thank you, Elaine. Hannah, any further questions?
Yeah, sort of a follow-on from my previous question. So I imagine that you're, and perhaps I missed you saying that you're working with some civil protection agencies on these debris flow maps. So from a sort of an influencing public policy standpoint, are there any particular visualizations or uncertainty summaries that resonated most with these non-technical stakeholders?
So it's not work that I've done, but at this volcano, just simulation footprints themselves. So no UQ involved. Plotted on the 3D map where you can turn it, was very, very popular with the civil protection. And so it's not here, but anything we produce will, our sort of GIS savvy colleagues will be putting it on 3D maps. And we're actually working have a colleague on this project at Edinburgh, Neil. I'm terrible at remembering names when I want to. His first name's Neil. In geography, who once we really get to the point where we feel like we have products, we're going to work with him to think about what the best presentation is. But yeah, it's really hard, I would say. You know, it's hard to not zoom in on a location to think about uncertainties and playing around with probabilities, right? So I guess I'm imagining sort of, you know, sliders of maps to maybe to sort of change your aleatory models. But then to really say here's the uncertainty in the aleatory model, yeah, I don't really have ideas on the best visualization for that. Could definitely use some help.
And are you, is some of those available open source, or are you open sourcing it in the future? Or
yes. So the ZGP stuff, I will do it this week. I'll put it on my website. My one of my students has our MATLAB versions on his GitHub. The spatial sampled version of it is still a work in progress. So hopefully my student Joey graduates this summer, and there will also be you know, packages available for that soon.
Yeah. Fantastic. Thank you.
Okay, I'm aware that we exceeded the hour we allocated for this webinar, and please join me in thanking our speaker, Professor Spiller, who joined us from the US, our first speaker outside the EU.
Yeah.
Whereas if we consider ourselves still in the EU, in the UK. But, so thank you, Professor Spiller, for sharing your very interesting work with us. And we would like to thank all those who joined us online. Our next webinar is scheduled on the 3rd of June at 2 p.m. British Summer Time. We have switched it from a weekly webinar to a monthly webinar, especially for the summer time where less people are around. We didn't finalize the speaker yet, so please watch out on the LinkedIn and on the YouTube channel for the formal announcement. Thanks again to our speaker and to my co-host, Professor Menke, and thanks for all who joined us. And see you next time.
Thanks.